Welcome again to mathematics. Today we are going to see an example of gradient descent with exact line search. So you will remember the idea of gradient descent to algorithmically minimize or maximize a multivariate function. The idea is to start with an arbitrary point, then compute the negative gradient at that point and follow that direction. The question here is, how far would you follow that direction? And one possible method here is to follow that direction to the lowest possible point along that line. And that is what is called exact line search. So we're going to demonstrate this here today using some Python code, specifically to make some plots so that you can see what actually happens here. Okay, so the code itself is not that important. We'll have a look at functions. This function here, so f of x1, x2 equals x1 minus 2 squared plus 2, x2 plus 1 squared plus 1. That's the function that we want to minimize. The gradient of that function is this here, 2x1 minus 4, 4x2 plus 4. And finally, I have also computed the Hessian. The Hessian looks like this. You have 2, 0, 0, 4. So you can easily see the determinant here of the first leading principal minor, that's 2. The determinant of the second leading principal minor is 8. So both are positive, and that means this matrix is positive definite. So a stationary point of that function here will actually be a local minimum. Okay, let's make some preparations for the plots. We'll first define this function as a Python function here, and the gradient will also be defined as a Python function, so we can compute that easily. Let's first have a look at how that function looks like. So let's see a surface plot. So this is the function here. You can clearly see it has a parabolic shape, and there seems to be a minimum somewhere here. Yeah, so around 1, 2, something like this here for the x1 direction, and somewhere around 0 and minus 1 possibly for the x2 direction. Okay. If you look at the gradient once more, you can of course compute that right away. You can see that setting x1 to 2 and setting x2 to minus 1 will give you the only stationary point of that function. Yeah, so the intuition from a plot seems about right. This becomes even more clear if we look at the contour lines here. So the level sets. This is a plot of the level sets. You can see we're starting with high levels out there, and as we're getting closer to this point here, the levels become lower and lower. So this point here is the minimum. Let's mark that. So again, you can see that is exactly at x1 equals 2 and x2 equals 1. So this is the minimum that we are looking for. We're going to start with the point minus 2, 2. Minus 2, 2, that's about here. And then see how gradient descent works. Okay, so this is step 1. First thing we do is we compute the function value at that point. And you can see that is the value 35. Okay, let's again have a look at the contour lines and mark that point here. So this is our starting point, and remember the blue point, that is the minimum. That's where you want to go. So we evaluate the negative gradient at that point, minus 2, 2, and we get 8 minus 12. So this here is the negative gradient. let's draw that direction. So if we're at that point and follow the direction of the negative gradient, we're walking along this line here basically. So we're going to make a step along this line. And what we want is we want to find the point along the line where the function value becomes minimum. So that's the exact line search. And that point is geometrically easy to find. That's exactly here at this point, where the line here touches one of the level sets. So this is where it touches the lowest possible level set. Yeah. Everywhere else, which cuts through the level sets, values become lower along that line or higher. But here it just touches. It's a tangent line to that level set, and that's where the lowest point is actually achieved. So this is the point that we want. And of course, we can also determine that by a small calculation. So our new x1 is of that form here, minus 2, 2, the starting point, plus some step size lambda times 8 minus 12. So the gradient, the negative gradient. You will notice that I have not normalized this negative gradient as I did in the algorithm. That's because we are doing exact line search anyway. So the normalization does not really matter. It's just the direction that matters. If I normalize that, then we will of course get a different step size, but the resulting point will be the same. Yeah, so if you're doing exact line search, you can do that without normalization. If you're doing heuristic line searches, heuristic step size selection, then normalization might be important. Okay, so that's the point that we are going to get, depending on lambda still. Then we have this g of lambda, so that's the function value depending on our choice of lambda here. V is the search direction, so the negative gradient. So g of lambda is the function f evaluated at minus 2 plus 8 lambda and 2 minus 12 lambda. And you can just compute that. You can then determine the minimum of g. And what you find is roughly a value of 0.3 for lambda. It's not quite exact, but it's just as close as we want it to be. Okay, so the new point x1 is about 0.4 and minus 1.6. So let's have a look at that in the plot again. So this here, this is precisely the new point that we want. And as I said, this is exactly where it touches the lowest possible level set. Okay, and from that point on, we're going to continue our line search. So the next step will again evaluate the gradient at that point. That's 3.2 and 2.4. Negative gradient is 3.2 and 2.4. And continue in that direction. So the new direction is the green one. And you can see that this direction is perpendicular on the old direction. Yeah. So the gradient is, from this point on, the gradient is again the direction of fastest local change, and of course that is orthogonal to the level set tangent. So we're now moving orthogonal to that again until we just touch the lowest possible level set, and you can't see that in the plot anymore, but that's something like here. So somewhere here that new point would be. And we just continue this zigzagging process until we get close enough to the point that we actually want. Okay, so that should give you an idea of how gradient descent works, and specifically how gradient descent with exact line search can be interpreted geometrically in the contour plot. Thank you for your attention.